Okay, this is the final video on Lagrange multipliers, and what I wanted to focus on is their physical interpretation. What's the interpretation of this number lambda that appears in the method? Okay, and so in order to put this into some context, some physical context, let's imagine the following problem, which is this projectile motion. Imagine that you have a cannon which releases a ball, so you have something here that can launch a projectile, and what we want to understand is the range of the balls that you're launching. So depending on when you throw your ball, it's thrown with a specific initial velocity in the x component and an initial velocity in the y component. So here, imagine that here's your ball. It has some initial velocity, that's why I'm putting a 0 here. And that has an x component and a y component. So you can think of this as like the initial speed in the x direction, the initial speed in the y direction. Right, and as you know from your physics classes, this will undergo some motion, which is like a parabola, and eventually it will land somewhere, and the place where the ball lands is like the range, right, of the projectile. So if you had chosen a different velocity, right, initial velocity like this one, maybe the range is out here. And if you had chosen a different initial velocity like this one, maybe the range is here. Okay? And so what we can define is that this quantity R for range, which depends on the initial velocities in the x and y directions. So this is the range of the projectile. And you can check if you have taken a physics class that the formula for this range is like a very simple formula coming from the fact that this is uniformly accelerated in the y direction. But so you just play around with that for a while, and you find that this equals 2 over g times v0x times v0y. So that's the formula for R. So again, we have this projectile, we're launching it at different velocities. The problem, I mean, maybe you're interested in knowing which combination of velocities you should use if you want this range to be as large as possible, right? So maybe you want to maximize the range. So here's the goal. The problem is that, as stated, this is not very interesting because you could just arbitrarily choose larger and larger velocities in one direction. Like, for example, imagine increasing like the x component of the velocity by an infinite amount, and so the range would just keep getting larger and larger. So in order for this problem to be physically interesting, you need a constraint. Okay. So and it's reasonable assuming that there's no friction or anything like that. Remember that if there's no friction, then there's conservation of energy. And assuming that, like, say if you fix a reference point where like the height is 0, where you're launching the projectile, then all the mechanical energy just equals the kinetic energy at the beginning. And so the constraint will be that however we choose to launch this projectile, we will launch it in such a way that the energies of the initial launches are all the same. So the constraint is that this quantity 1/2 of m v naught x squared plus v naught y squared, right? This is like the kinetic energy of the projectile. This quantity, we want to make it a fixed number. So I guess energy was like measured in joules, and so you may want to launch the balls in such a way that they're always being launched with 10 joules of energy, for example. So under different names, this function is really like f, and this function is really like the constraint. So this is like g. The only difference is that now we're using different letters for everything. And so the f, right, is again is this function 2 over g times v naught x, v naught y, and the g, the constraint equation, is this one. And notice that this is slightly less complicated problem in the sense that now we're just using two variables, x, like, so this is like behaving like x and y. We don't have like a z variable, so it's only two variables here. But still, the Lagrange multiplier method would say that the what you need to solve is just that the gradient of r has to be lambda times the gradient of g, and also the g has to be equal to 0. That's what the Lagrange method says. So let's try to figure out what that becomes in this particular context. Okay, let's go here. I don't want to erase that necessarily. Again, the gradient of the range is just the partial derivatives with respect to these variables, which are like x and y. Remember that g is like a constant, which is just like the acceleration to gravity. So the gradient of r is really 2 over g times v naught y, 2 over g times v naught x. And then the gradient of g. Okay, so now, sorry, I should have called this, I will call this equation Z for constraint because I already used the letter G for acceleration. So let me, okay, let me call this C for constraint, and now we're good to go. Good. So the constraint equation is that this must be equal to 0. So the gradient of the constraint equation is just that, again, you take the partial derivatives with respect to v naught x and v naught y. With respect to v naught x, you get m v naught x, and with respect to v naught y, you get m v naught y. So those are the two gradients, and so the system that we must solve is the following. We must solve this one equals that one times some multiple, so we need 2 over g v naught y equals lambda m v naught x. We also need 2 over g v naught x equals lambda m v naught y. Right, so those are the equations that come from the gradient. And finally, we need the usual constraint equation, which is, well, I'll keep writing it here. So again, this is like 1, 2, and 3. And the problem becomes one more time about deciding how you want to solve this system. If you go back to the box problem, you will notice that this is very similar because these two right-hand sides are almost the same, right? What's missing here is v naught y, what's missing here is v naught x. So what we will do is multiply 1 by v naught y and 2 by v naught x. And if you do that, you end up with the system I really want to work with, which is the following. So when you multiply the first equation by v naught y, you get 2 over g v naught y squared equals lambda m v naught x v naught y. When you multiply the second by v naught x, you get 2 over g v naught x squared equals lambda m v naught x v naught y. And the last equation, which continues to be the constraint equation, is just that 1/2 m v naught x squared plus v naught y squared equals e. So we need to solve this system. In order to solve this system, again, you can equate the right hand sides here. This equals this. So here they are the same. And so that tells you that the left hand sides have to be the same. So 2 over g v naught y squared equals 2 over g v naught x squared. And that tells you, right, you can cancel the 2 over g on both sides. That tells you that v naught y squared equals v naught x squared. And again, you would take square roots. Usually you get a plus or minus, but here you're imagining from the context of the problem that the velocities are all positive, so that it makes sense. And so you conclude that v naught y equals v naught x. So again, what that means is that if you're launching the projectiles with a fixed kinetic energy, right, then in order to maximize the range, you have to throw this in such a way that their initial speeds in both directions are the same. And so that really tells you that the initial angle has to be 45 degrees, right? And notice that in this case, we can specify these initial velocities in terms of the constraint. Because now, once after we know they are the same, you can say, well, so 1/2 of m times m of v naught squared plus v naught x squared plus v naught y squared. But they're the same, so you get 2 v naught x squared equals e. And so again, from here you can say that v naught x equals v naught y, and solving for this you get square root of E over M. Okay? So in terms of the kinetic energy that you had to use for launching the projectile, you can figure out their velocities. Okay? And notice from here, well, there's two things that we can say. First of all, let me go. This is like an example where the Lagrange multipliers, again, you did not need to find, right? We never computed what lambda is supposed to be. And so, what would lambda be in this case? Well, I guess lambda, after we know that lambda, that both velocities are the same, you can say, for example, that lambda equals 2 over g times v naught y squared over m v naught y squared, right? And so let me write it here. So what I'm trying to say is that using the equations you can find that lambda is really nothing but 2 over g times m. Okay, and like even just this formula is like more interesting. For example, it has units of weight, or 1 over weight, right? Inverse units of weight. Maybe that's not something one would have imagined. More importantly, notice that this is really independent of E. Right? It just depends on like fixed variable, fixed constants, fixed parameters like universal parameters like the mass of the particle that you're using for launching, for throwing it, and then the acceleration due to gravity. Okay? But still, this is not quite the meaning that I'm after for this Lagrange multiplier. So let me tell you how you can think about this. So again, we had this problem. In this problem, we were allowed to vary the initial velocities, right? So long as E was fixed. So here, velocities could change. But E was fixed. Now I'm going to do something slightly different, which is the following. Imagine that you still have the same projectile problem, but now we already know that if you fix the energy and choose an angle of 45 degrees, then the range is maximum. So imagine that for each particular value of energy, right, you're launching this projectile. So maybe this is a trajectory that you get by choosing an energy of 10 joules. So again, this is maybe at 45 degrees. Maybe there's another one which again is at 45 degrees. But now you're using fewer energy, less energy, so you're using 5 joules. Okay, but again, notice that you're throwing it at 45 degrees. And maybe now you're using, again, the same angle, initial angle, but now you're using more energy, so maybe now you're using 12 joules. So now what I'm doing is throwing the balls at the same angle, so fixed angle. But I'm letting E vary, okay? So now what is changing is that this quantity, which before was a constraint, okay? And now the range becomes a function of E, right? Because depending on the energy that you choose, the range will be different, as you can see here. So now I want to think of the range as a function of E. And again, the original formula for the range was this one, but you know that each of these, right, can be written in terms of the energy. So this gives you root of E over m squared. And so, in other words, what you find is that the maximum range, let me just specify this. So the formula that I'm after is that the maximum range that you can get with a fixed, by using some energy E, right? If you square this, the square roots go away, and so you just get 2E over Gm. Okay, so again, for a fixed value of E, this is just denoting the range that you get by using 45 degree angle lunge. And what's interesting here is that this is a maximum range with respect to this constraint parameter. So what you should notice is that if from this point of view, it becomes like a function of E, so you can take the derivative with respect to E, and you find 2 over Gm, which is okay. You may say, well, this is just like some quantity, but that happens to be exactly the Lagrange multiplier. So what's the physical meaning of lambda? So what this means is, and this is usually what happens in general, not just in the specific context, even in economics there's like an interpretation along these lines. But so what is the meaning of lambda? So the meaning of lambda is that lambda is the rate of change of what? Of the quantity you were optimizing with respect to what? With respect to the parameter that you were fixing throughout the problem. So with respect to the constraint parameter. Okay. So again, the takeaway from this example is that lambda is really a rate of change. It's not something that we would necessarily use for the course, but it's something to keep in mind in case you ever run again into Lagrange multipliers.